I still lose sleep over this fact.
Okay.
I still lose sleep over it. And I want you to lose sleep too. I don't want to be the only one staring at the ceiling at night.
I'm going to tell you, a lot of things already beat you to that.
Oh, sure. I mean, the asteroid strike that could happen, or the
exactly.
right, or the global warming, or all right.
Yeah.
So here it is. You may remember, or you may have heard, that Einstein's relativity,
Right.
more specifically, you learn this in special theory of relativity, where the faster you move,
Right.
the slower time ticks for you
Right.
as others view it.
Relative to the observer.
Relative to the observer, correct. You don't know anything's happening.
Right.
Your clock still ticks as far, you still got your heartbeat, all of this. Okay, so this is not a physiological thing. It is an actual property of the fabric of space and time under those conditions.
Wow.
Okay?
That is fascinating.
It is. It's completely fascinating. It's completely. So I watch you fly by, and the faster you go, the slower time ticks for you. Okay?
But my time stays the same.
To you.
To me. Right.
To you. So not only does speed do this, also the strength of a gravitational field will have this same effect on you.
Oh.
The stronger the gravitational field is, the slower time ticks for you. Oh. And that wasn't formulated until his general theory of relativity 10 years later. That took a lot more math and deeper insights into the universe.
But once again, it makes sense because you're dealing with the fabric of space-time.
It's the fabric of space-time, correct.
Wow, okay.
But initially, when formulated, you're thinking it's just because you're moving.
Right.
But it's actually way deeper than that. And that's why that one, oh, by the way, his original special theory of relativity was not called that. The title of the research paper was On the Electrodynamics of Moving Bodies.
What?
Okay, that was the title. We would later call it the special theory of relativity because it was a special case of what would later then be called the general theory of relativity. While we're there, let me just slip this in. The GPS satellites orbit higher than like the space station and other things that are in what we call low Earth orbit.
Low Earth orbit.
They're in like MEO, middle Earth orbit. There's LEO, MEO, and GEO. Okay.
Right.
If you have kids, maybe you name them that.
Yes. Leo, Mio, and Geo.
Low Earth orbit, middle Earth orbit, and geosynchronous geo orbit. Okay, right. So the geosynchronous satellites are like middle orbit. That is far enough away from Earth's source of gravity for them to have a measurably different space-time condition.
Oh.
So that their clocks tick faster than our clocks on Earth's surface because they're farther away. And so remember I said the more intense the gravitational field is, the slower time ticks. So they're farther away. Their time ticks faster relative to us.
Wow.
But we get precise timings from geosynchronous satellites. So how does this work? We pre-correct the time signal from the GPS satellites to compensate for Einstein's general theory of relativity so that by the time the time reaches us, well, it's been properly corrected and it matters to us and our space-time continuum, not the one that's in middle Earth orbit.
Oh my goodness.
So GPS couldn't work as accurately as it does.
However, wait a minute.
What?
I'm sorry, just for me, you would have to have a standard in order to pre-correct something.
You know the rate at which its time is speeding up because you can calculate what the gravitational field is up there.
There you go. Okay.
And once you calculate that, then you do and you say, oh my gosh, the formula works. Einstein was right.
Right.
All right. This is not just something on a high theory, hypothesized that may or may not be true. It is true.
I just want to be there when that phrase is uttered. Oh my God, Einstein was right.
Yeah, these aren't just cult heroes that we wish they were right. These are real. This is real. Okay, this is the real universe we're talking about here. Okay, so now watch. Let's keep going faster and faster. Okay. Let's go half the speed of light, three-quarters the speed, 90% the speed of light, 99% the speed of light. Mm-hmm. Time is ticking slower and slower and slower. For you, you will watch the whole future history of the universe unfold in front of your eyes as fractions of a second go by for you. As you go 99, there's a formula for this, of course, but 99, 99.9, 99.99% the speed of light.
Because you're the observer of that.
Of that.
For you, your time has slowed to the point where as you observe the things that are not moving at the speed of light, you see them
Speeding,
basically,
correct.
you see
Speeding
them
up.
unfold.
Correct.
Boom. God.
Correct.
That is insane.
So now watch.
Oh my God, wait.
Now watch. Okay.
Wow.
So I didn't even get to the part where I lose sleep.
Okay.
Okay. That's what happens. By the way, there are particles that decay. You've heard of like radioactivity, right?
Yes.
It's one part, it decays and becomes another part and releases often deadly energy.
Yes.
Okay. Radioactivity. All right. Some particles, let's take, for example, the proton or the muon. One of these it decays in like 6 minutes when it's left out in the wild. Okay. When it's not part of an atom.
Okay.
When it's not in captivity, I forgot which of these, but it doesn't matter for my example. Decays in like 6 minutes, okay? Okay. What happens if you take that particle and speed it up in a particle accelerator? So you take a community of these particles, speed them up, calculate, wait a minute, the internal wristwatch on these clocks says they should live longer. And sure enough, their decay time takes longer.
Wow. That's, oh my God.
Yes. Yes.
Oh, wow.
Yes.
And that becomes living proof of what Einstein said.
Yes, because we can't go half the speed of light.
Right.
But you can accelerate a particle to do that.
Yes.
And it has an internal built-in clock that decays after a certain amount of time, and there they are taking longer to decay in the exact amount that Einstein predicts.
That is genius.
So we don't make this stuff up, okay?
Yeah.
Yes, it is genius. It's like triple genius. All right. Now, let's take this to an extreme level.
Right.
Let's go so fast that we're going the speed of light itself.
Right.
Well, we can't do that because we're made of material substance, and there's no way to do that. But there are things that travel at the speed of light. And what is that?
Those would be photons.
Yes. Thank you. I like those would be, I like your finger gesture. That would be, I would say, what travels at the speed of light? Light does.
Yeah.
Okay.
I was about to say light.
So if photons had a clock, the clock would never tick.
Nice.
Which means when I go to a mountaintop, as I did in graduate school, to observe the center of the Milky Way galaxy for stars that emitted their light 30,000 years ago, traveling through the gaps of interstellar space, and they move through space, come through Earth's atmosphere, they come down into the telescope, they reflect, go back to my detector, and land on my CCD chip. That photon, when it was born, at the star that emitted it, was detected at my telescope in the same instant.
Wow.
According to the photon itself.
Live fast, die hard.
The photon has no knowledge of that trip.
Right.
Because time did not exist for it.
Oh, that's great.
And I'm saddened that many of these photons like hit people tanning on the beach, you know, and imagine traveling 30,000 years and land on someone's buttocks.
Yep,
when
very
you
sad.
With the telescopes I collected, I'm now decoding the nature of the universe. And some photons go right on by Earth and are still moving, but they have no internal time clock.
Wow. And they're just traveling through like, I hope when I'm born, I hit a telescope.
Bam! You're born and you hit a telescope. That would be an interesting, but what do I want to be when I grow up? Or, or the instant I am emitted, where am I going to be
Where
absorbed?
would I like to be? Yeah.
Right. And so just the idea that light can move across the universe and have no, and not age. This is a fascinating fact to me.
Wow.
Yeah.
That is more than fascinating. That is,
Yeah.
I mean, that's mind-boggling.
Yeah. So that is light, the age of light. It's like it doesn't age at all.
I am convinced that all of you guys secretly microdose and smoke weed. That's
another episode. That's what I'm saying.
Another episode.
All right, Chuck, we're calling it quits there.
All right.
Mysteries of light and time. Neil deGrasse Tyson here. Keep looking out.